Good morning. So this video is about FIR filter design. So when it comes to FIR filter design, we have two methods for designing a FIR filter. Okay. So one is called as windowing method. Second one is called as frequency sampling method. Okay. So first we'll start with window method. So basically, what is a window method? Okay. So that's what we're going to see. Okay. So for that we'll start with the ideal low pass filter response. Okay, so just consider an ideal response. So ideal filter response, this is how your low pass filter actually looks like. Okay, so this is a WC, this goes up to pi. Okay, this is HD of e power j omega, that's the frequency response, right? So similarly you'll have I'm putting it in the negative also. Okay, so minus omega c, this is minus pi. Okay, so we can write HD of e power j omega is equal to 1 when omega is greater than 0, less than omega c, it is equal to 0 otherwise. Okay, now we'll try to design a filter. So basically this is the frequency response that is desired. Okay, a low pass filter frequency response that is desired. We try to take the inverse of this. This is HD of n. So HD of n is 1 by 2 pi. It is minus pi to plus pi. So HD of e power j omega, e power j omega n d omega. Okay, so if you take the inverse of it, so even though the limit is from minus pi to plus pi, for our signal it is from minus omega c to plus omega c. Okay, so minus omega c to omega c, the value is 1 e power j omega n d omega. So if you integrate this, so it is e power j omega n, we are integrating with respect to omega. Okay, so it is j n, so minus omega c by omega c. So this we can write it as 1 by 2 pi j n e power j omega cn minus e power minus j omega cn. Okay, so what is e power j theta minus e power minus j theta? Okay, so it is nothing but 2 pi, sorry, 2j into sine omega cn. Okay, so cancelling out all the pi 2j terms, you will get sine omega cn by, okay, so j gets cancelled, so it is n pi, sine omega cn by n pi. Okay, so sine n by so in omega c by n pi, so where n expands from minus infinity to plus infinity. Okay, now actually if you take the inverse, if you draw this curve, okay, if you draw this curve, so it actually looks like this one. So it will have a central thing. Okay, so my signal actually goes like this from minus infinity to plus infinity. So the signal actually goes like this. So see, this is an infinite signal. We clearly know this is an infinite signal, but what we want to design is a finite impulse response. What we have got is an infinite impulse response. How can we make this as a finite impulse response? This is infinite. If you want to make this as finite, a better option is one of the option, not a better option, one of the option is you can truncate it. You can truncate it so that it gives you a finite output. Because this is infinite, you try to truncate it so that you get a finite. Okay, how can you truncate this? Say this is your hd of n. Hd of n, you multiply this signal with something called as a window function. Okay, so this window function, I'll just put it like this. Okay, so this is a window function which is of limited range. This windows function is of a limited range, which is from minus n minus 1 by 2 to n minus 1 by 2. Okay, if you multiply these two signals, what happens? Now your signal is a finite range, because beyond this it is 0 for this windows function. Beyond this range it is 0. So if you multiply these two signals, this is red and green, so this is the resultant will also be what will be my result? What will be my result? My result will be something like this. If you multiply these two from this diagram, I'll be getting something like this. Okay, so the range is from minus n minus 1 by 2 to n minus 1 by 2. Okay, so you're abruptly cutting by multiplying it with the window function. What happens whenever you do this kind of an abrupt cutting? Okay, there will be some implications, right? So there will be undesirable ripples, okay, undesirable oscillations in the pass band as well as the stop band. You will have undesirable oscillations in the pass band and stop band. These undesirable ripples or oscillations are called as, or this is given by the name called Gibbs phenomenon. This is called as Gibbs phenomenon. Okay, this is called as Gibbs phenomenon. And this method of creating a finite impulse response filters by multiplying window function with your infinite is called as windowing method. It's a basic concept of windowing method. Okay, and by each windowing, there are different windows available. By each windows, what we try to do is we try to reduce these oscillations. Okay, so basic window is this one. This is called as a rectangular window. Okay, so the rectangular window, if I put it in a proper equation form, okay, so the equation actually looks like this. So if you define your equation for your rectangle window, so the first window is a rectangular window. So rectangle window is given by, so WRN is equal to, basically it is 1, okay, for the range of minus n minus 1 by 2 to n minus 1 by 2. Okay, it is equal to 0 otherwise, that's obviously. Okay, so still if you want to cut down the oscillations, okay, so instead of having a gradual cut, instead of having an abrupt cut, we can have a gradual cut. Okay, so this is called as triangular window. So in triangular window, instead of abrupt cut, we have a gradual cut. It will be somewhat smooth. Okay, so Wt of n is given by 1 minus 2, so mod n by n minus 1, and again the range is from minus n minus 1 by 2 to n minus 1 by 2. Okay, this is for triangle window. Still, if you want to reduce the oscillations further, okay, we add one more cosine term into it. Okay, so this is called as raised cosine term, raised cosine window. Okay, raised cosine window. This is still for smoothing further. You smoothing further by using a cosine term. So this is given as alpha plus 1 minus alpha cos 2 pi n by n minus 1, where n ranges from minus n minus 1 by 2 to n minus 1 by 2. Okay, and for specific values, say there are a lot of other people who have contributed. Then we have Anning window. Okay, Anning window is nothing but in the raised cosine window, if you substitute alpha is equal to 0.5, if you substitute alpha equal to 0.5, you'll get an Anning window. So Anning window is given by, so 0.5 plus 0.5 cos 2 pi n by n minus 1. Again the n ranges from minus n minus 1 by 2 to n minus 1 by 2. It is equal to 0 otherwise. Okay, this for an Anning window. So this is particularly at high frequencies. Whenever the stop band attenuation is great, we can go for an Anning window. Okay, so this is particularly suited. So at high frequencies, when stop band attenuation is more, okay, stop band attenuation is great. Okay, so for those cases we can use an Anning window. Okay, and the third next variation is called as Hamming window. You call it as an Hamming window, Mming. Okay, the previous one is an Anning, this one is an Hamming. Okay, so WHM of n. So in this case you take alpha as 0.54, that is in our raised cosine window. If you take alpha is equal to 0.54, you will get Hamming window. So it is 0.54 plus 0.46 cos 2 pi n by n minus 1. Again n ranges from minus n minus 1 by 2 to n minus 1 by 2. Okay, it is equal to 0 otherwise. And the last window is a Blackman window. Blackman window. So Blackman window is, you have an additional cosine term, okay, so that it reduces the side lobe further. Okay, you have additional cosine term, so we'll have WB of n is 0.42 plus 0.5 cos 2 pi n by n minus 1 plus 0.08 cos 4 pi n by n minus 1. Again n ranges from minus n minus 1 by 2 to n minus 1 by 2. Okay, so all these windows are basically trying to reduce the Gibbs phenomenon. Okay, so what happens in a Gibbs phenomenon, you get these undesirable oscillations. Okay, so basically if you see the pass band and the stop band, it has to be ideally like this. Okay, but due to the abrupt cutting, so you'll have oscillations, so this is actually the Gibbs phenomenon. And different windows, we try to reduce these Gibbs phenomenon. That's how we design an FIR filter by using a windows method. Okay, thank you.